By the end of this lesson, students will be able to explain why metals are good conductors, explain how metallic bonds are formed by the overlapping of atomic orbitals, explain the formation of valence band and conduction band, distinguish between conductors, insulators, and semiconductors in terms of the energy gap between the conduction and valence bands. In this lesson, we shall discuss the bonding present in metals and how this bonding gives special properties to metals. Consider the structure of aluminium. Here we see a closely packed lattice of atoms of aluminium. Now click on the Structure button. In this structure, we observe that the metal cations are surrounded by a sea of delocalized electrons. Delocalized electrons are the valence electrons which are not held strongly by the nuclei and are easily removable. Therefore, these valence electrons are free to move in the lattice. This results in metallic bonding. Metallic bonding takes place due to forces of attraction between the cations and the delocalized electrons. To see the conduction of electricity by aluminium, click on the Circuit button. Click on the aluminium metal to see the movement of delocalized electrons towards the positive electrode. Conduction takes place by the movement of delocalized electrons. To understand the concept of bonding and electrical conductivity of metals, we need to look at the formation of orbitals that extend over more than one atom. Such orbitals are called molecular orbitals. To understand them, click on Activity 1. In this activity, we are going to explore the molecular orbital theory. When two atomic orbitals combine, they form a set of molecular orbitals. One is the bonding molecular orbital and the other is the antibonding molecular orbital. A bonding molecular orbital has a greater electron density between the nuclei of bonding atoms, whereas an antibonding molecular orbital has zero electron density between the nuclei. A bonding molecular orbital will have lower energy than the antibonding molecular orbital. Look at the energy levels of the molecular orbitals of hydrogen. Which orbital is more stable and why? Answer: the bonding molecular orbital is more stable as it has lower energy. The two electrons are filled in the bonding molecular orbital with opposite spins, thus obeying Pauli's exclusion principle. In the case of metals, the delocalized electrons move freely through the bands formed by the overlapping molecular orbitals. This is explained by the band theory of metallic bonding, which we shall consider in the next activity. Atomic orbitals overlap to form two types of molecular orbitals, namely bonding and antibonding molecular orbitals. Bonding molecular orbitals have less energy than the antibonding molecular orbitals. Sodium is a group 1 metal with a 3s1 valence electronic configuration. Click Next to see the formation of molecular orbitals formed by the overlap of the 3s orbitals of two sodium atoms, Na2. Click Next for 4 sodium atoms, Na4. What can you deduce about the number of molecular orbitals formed? Answer: the number of molecular orbitals formed is equal to the number of atomic orbitals combined. Click Next for 10 sodium atoms, Na10. The molecular orbitals are so closely spaced that they are best described as a band. This band here is called the 3s band. Click on Fill Electrons. What can you say about the 3s band of sodium? Answer: the 3s band is only partially filled. This band is also called the valence band as it contains the valence shell electrons. The orbitals associated with all the energy levels in this valence band extend throughout the solid. However, the electrons in the 1s, 2s, and 2p orbitals are localized on each sodium atom. Sodium has high electrical and thermal conductivity. Discuss and click Next. Sodium is a good conductor of electricity as the electrons in its valence band can move from atom to atom easily. This is possible as the valence band extends throughout the metal lattice and is only partially filled. In sodium, the valence band is the conduction band. Magnesium is a group 2 metal with a 3s2 valence electronic configuration. The diagram shows the energy levels of the molecular orbitals of the 3s band of Mg4. The 3s band of magnesium is not a conduction band. Why is this so? Click Fill Electrons button to help you figure out the answer. Answer: the 3s band is filled. Electrons cannot move through the solid because orbitals in the same band on neighboring atoms are already filled and cannot accept an additional electron. What will be the conduction band of magnesium? Click Next for the answer. Any band that is empty or partially filled and uninterrupted throughout the solid can act as a conduction band. For magnesium, the 3p band formed by the overlap of 3p orbitals is empty and so it acts as the conduction band. Is there any energy gap between the bands? Click Next for the answer. Answer: the energy levels of the conduction band overlap with those of the valence band in magnesium. So, there is no energy gap between the bands. How does magnesium conduct electricity? Click Next for the answer. Answer: as there is no energy gap between the conduction band and valence band, the electrons are easily delocalized from the valence band to the empty conduction band. This accounts for good electrical and thermal conductivity of magnesium. Sodium is a good conductor of electricity as the electrons in its valence band can move from atom to atom easily. The valence band of sodium is the conduction band. There is no energy gap between the conduction band and the valence band in a metal like magnesium. Electrons are easily delocalized from the valence band to the conduction band. Substances which conduct electricity readily are called conductors. In the case of diamond, all the valence electrons of carbon are used to form covalent bonds. So, all the orbitals of the valence band are filled and cannot contribute to electrical conductivity. Unlike magnesium, the electrons in the valence band cannot move into the conduction band easily. Why is this so? Discuss and click Next. Answer. There is a large energy gap between the filled valence band and the empty conduction band. A large amount of energy is needed to promote an electron up into the conduction band. Silicon is normally not a conductor, but will conduct electricity when it is heated. Click the Heat button. Why is this possible in silicon and not in diamond? The energy gap is smaller in silicon than that in diamond. Substances like silicon, which can conduct electricity at elevated temperatures, are called semiconductors. You can now see the conduction and valence bands of three different types of materials. Drag the correct word into the boxes below each of the energy diagrams to indicate which diagram represents the bands of a conductor, an insulator, and a semiconductor. Substances which are poor conductors of electricity are called insulators. Insulators have a large energy gap between the valence and the conduction bands. Substances like silicon, which can conduct electricity at elevated temperatures, are called semiconductors. The energy gap between the valence band and conduction band is smaller than that in an insulator.